Hey, welcome back to Math with Patrick. Today is November 12th. I do have Quill with me still. He's joining us and helping out with some math. And we're solving problem 316 from the Daily Epsilon calendar. And today it looks like we have kind of like an intro to calculus problem. We have a function f of t, which is just the cube root of t. And our answer today should be the derivative of our function evaluated at 1 over 216. To kind of explain what's happening here, so this is just the cube root function. This inputs, say, a number 8, and then it outputs the cube root of it, or the number where multiplied to itself 3 times over gives you that 8. So for this one, if we plug in an 8, we can cube root it, and that gives us 2, because 2 times 2 times 2 is 8. And so what this function does is that it essentially takes big numbers and then turns them smaller. And so you could imagine if we plug in, say, an 8 here, we're only going to get an output of 2. If we plug in a 1, we get a 1 because the cube root of 1 is 1. So that would look something like this. The cube root of 0 is 0. And then if we think about negative numbers for a sec, if we try f of negative 1, that's going to be the cube root of negative 1. And again, this asks, can we find some number where when we multiply it to itself 3 times over, we get this target number? And yes, we can. It's just negative 1 itself. So we're going to get another point right there. And then maybe you can kind of see some symmetrical pattern happening right here, where we are going to just mirror the first quadrant, or I guess rotate the first quadrant into the third quadrant, and we are going to get a point at like negative 8 and then negative 2. And so this is the picture of our cube root function. And the derivative just measures the change or the rate of change at any moment on this graph. And it looks like we want to find the rate of change, or the slope, when t is 1 over 216. So we would have to zoom in real far at the origin to see what's happening here. Again, we still have this point 0, 0. And locally here, there's actually going to be a vertical slope right at the origin, and then it's going to kind of peter off in either direction like that. And so this 1 over 216 is going to be incredibly close to 0, something like this. And looking upwards, our slope here is going to be fairly positive and fairly large. So that kind of bodes well for an answer that's supposed to be 12 today. To find the actual value of the derivative, well, we need to take the derivative of the function. I'm going to rename f of t using an exponent. Instead of the cube root of t, I'm going to use t to the power of 1/3. And now I'm set up to just use the power rule here, f prime of t. So we drop this power as a coefficient, and then we subtract 1 from this power. So now it's negative 2/3. And then now all I need to do is plug in this 206, or 1 over 216 rather, into my kind of gross negative fractional exponent. And then let's interpret what this negative fractional exponent is doing. First, negative exponents tell you to divide, so one way to get rid of them is just flip the argument or the stuff on the inside. So I can get rid of that negative exponent as long as I flip or take the reciprocal of what is on the inside. Fortunately, that's pretty easy. That's actually just the number 216. Divide by 1 doesn't really do much. Now, to evaluate this fractional exponent, I like to take it in 2 steps. This 2 up here tells me to square it, while this 3 down here tells me to cube root it. Kind of the same idea as like this before, where the power of 1/3, this 3 came from cube rooting, essentially. And so here, I think I'd rather cube root it first. I do know that 6 times 6 times 6 is 216, so the cube root of 216 is just 6. This square is still there. Let's evaluate the square. That's 36. And then finally, we can multiply by 1/3, and we do get 12. So we're done. I do want to show one more thing, though, and that maybe you'd want to avoid all of this fraction arithmetic. These negative and fractional exponents are kind of tiresome to deal with. And so one thing we could have done from the beginning is actually thought about our inverse function. The inverse function, which I'll write maybe f inverse of t, I think for simplicity, I'm just going to rename that to g of t, is going to be the opposite operation of cube rooting, which is just cubing. And these two graphs, the cube graph and the cube root graph, are going to have a similar shape. And so if we ask questions about the slope of one, we can probably get answers about the slope of the other one. The cube root graph looks somewhat similar to the cube, so the cube graph looks similar to the cube root graph. Instead of a vertical tangent at the origin, we have a horizontal tangent, and then we swoop upwards to the right or downwards to the left. This value of 1 over 216 no longer is an x value, but that's going to correspond to a y value right here. And the corresponding x value, we got to think, well, f of what is going to give us 1 over 216? Well, if we're cubing stuff, then we could take that fraction 1/6, cube that, and again, 6 times 6 times 6 is 216. So if I learn something about the slope of x cubed at this point, 1/6 comma 1 over 216, I'm going to learn something similar about the slope of the original function. And inverses have this fun property where their slopes are reciprocals of each other. And so we just learned that the slope here is 12. And so if we seek out this slope right here, we should get a 1/12. This kind of comes from the fact that slope is just rise over run, y over x. And then inverse functions swap our inputs and our outputs. And so if we swapped x and y, we're just going to get x over y instead of y over x. And so this shows me that the slopes of inverse functions are going to be reciprocals of each other. So it's a lot of like conceptual stuff, kind of front loading this concept, but I do think that the derivative is going to be a little bit easier for our inverse function. G of t is equal to t cubed. I was going to write x. Using the power rule again, we can say that g prime of t is equal to 3t squared. And then now I should plug in this 1/6 because that's my t value, see what happens. G prime of 1/6 is equal to 3 times 1/6 squared. 1/6 squared is 1 over 36. Times that 3 gives us 1/12. And then finally, we can use that idea that I erased over here, where the slope of the inverse function and the original are going to be inverses of each other at kind of these like corresponding points. So I could just flip this 1/12 and I would get the 12 that I got before. I think it took longer to explain the inverse function idea, just because there are a lot of, again, steps at the front to kind of conceptually think about it. But I was actually able to solve this more quickly and find this 12 just because, like when I did this on my own, just because the derivative here was so much more easy to use. So it's kind of a trade-off. It takes a little bit to learn about derivatives and inverse functions, but maybe you can do that so you can avoid kind of nasty derivatives like this one. Either way, we get 12 for today, and I think we're all done. So thanks for watching, thanks for coming along, and I'll see you tomorrow. Bye.